Oh, no, that's
Okay.
fine. So the evaporator makes the refrigerant absorb the low level heat recovered from the energy pipe. And basic heat pump is usually 3 to 4 times efficient. So for every dollar of electricity you put in, you're going to get $1 of heat, or $4 of heat, or $4 of cooling. So it's very efficient. And if you were just using a straight air conditioner, for instance, in California, we don't need it right now in Sudbury, but if you were using an air conditioner, for every dollar you use for your air conditioner, you'd get $1 of cooling. If you had a heat pump, you'd get $4 of cooling. And so that's where the efficiency comes. Now, I don't know if you can move on a little bit, John, to the geothermal. The geothermal, the one thing with geothermal is that if you have pipes embedded in the ground, it's at a constant temperature all year round. Whereas with an air-to-air heat pump, it varies. Of course, and it's cool at certain times of year, and it's very warm at other times. Geothermal, if you go down 6 to 10 feet in the ground, it stays almost the same temperature all the time at about 55 degrees, 57 degrees Fahrenheit. So the efficiency there is that if you wanted to heat the home, you're bringing this, you're pumping solution through these pipes in the ground, bringing it into your geothermal heat pump, and you're bringing it up from, if you wanted the room at 70 degrees, as I think someone had just said they turned up the temperature, you'd bring it in at 57, you would only require enough energy to bring it from 57 to 70 degrees, so 13 units. Same with cooling. If you wanted to cool it down, if it was 80 degrees out and you wanted to bring it down to 70, you'd only have to have 10 units of energy in order to cool it down. And somebody says, well, how does this work? It's basically, it's a little magic. It's called a TX switch. And it switches from one cooling to one to heating. It goes back and forth automatically. So you set the temperature in your house at 70 degrees and you leave it. Now in Canada, it's very efficient because, in fact, the other day at my home here, I have a heat pump, and it was, I think it was only about 8 or 9 degrees above, and it was heating my home with that. And ordinarily, we'd have to use natural gas, but I had an efficiency of about 400% on the energy that I was using at that time to heat my home. So the heating bill, of course, is so much lower. Now, the next thing that we went a step further, ordinary geothermal, I mentioned that there's pipes buried in the ground 6 to 10 feet down where we circulate a fluid through. You can circulate, you can take well water where you're taking the water out, taking energy out of it, putting it back in another well. You can have it circulating in a lake, taking the water out, putting the water back in. What we do with our geothermal at source pipe is that we have a heat exchanger embedded, and John will go into this in detail after. We have it embedded in the walls of our concrete sewer pipe. So the effluent goes down the sewer and it heats up the pipes, and we take the energy out of it by circulating a fluid in our heat exchanger around in the pipes and bringing it back into the geothermal heat pump. So we do that. Plus, we also use the surrounding ground as a heat source that we can take energy out of it or put energy back in, as I was saying before, for cooling. So we use it both ways. And it's very efficient because the system's already there once you install it, and you don't have to install a separate unit for geothermal. So that's a basic principle of it. You can go into detail, but all it involves is a condenser and an evaporator, and it's a very simple system, whether it's a heat pump or a geothermal heat pump. I don't know.
Les had described a little bit of the system that we have. Here's a little more detail. It sort of shows a house on the right-hand side of your screen with a heat pump, and the heat pump then circulates its fluid. And I don't know, I guess whoops, I don't even see my mouse on here. The heat pump circulates its fluid anyways down here and down this line here, and it goes into the sewage into what we have as heat recovery system embedded in the walls of our sewage pipe. So here's a string of sewage pipe that's in front of the home right there, and the fluid goes around these sewer pipes, and what it does, it captures any thermal energy that is in the effluent in the sewage pipe. The nice thing about our system is that since it's in the walls of the sewage pipe, it will also capture heat from the soil around the sewage pipe. So if the soil around the sewage pipe is warmer than the sewage effluent, then they're capturing it from the soil as opposed to the sewage effluent. The system then takes it back into the house and back into the heat pump, and the heat pump then distributes that heat throughout the house. Probably if you're looking at a system in California, you probably would not have to put in a supplementary heat system. In Northern Ontario, if you only have 50 feet of frontage on your house, there might not be enough sewage pipe there to provide the energy required to heat your home. So in that particular case, we could supplement it with in this particular case, we show a well that is in here, but it could be, in any type of an in-ground heat recovery system that is there. And we have valve boxes. I don't know how the water system works in California, but in Canada here, we have valve boxes at the lot line. So at any time, the city could come in and turn your well off or turn your water off or turn it on again. Same system with here is that you can turn the system on or off with these valve boxes that are at the water line. I just did a sort of a rough calculation here looking at a system where you have 500 houses upstream and with a 12-inch diameter sewage pipe. And again, this is here's in Northern Ontario. So it's going to be a little different sort of where you are. As I say, you're probably not going to need any geothermal wells. So in this particular case, the first 6 houses on here do not need a geothermal well. There's enough heat coming through the sewage pipes, and that's with 500 houses upstream. And following that, then we're having to start drawing some heat from geothermal wells to supplement the system. Now, the geothermal wells, in this particular case, I show a geothermal well. I'm trying to find my mouse here. I throw a geothermal well at each one of the houses. It doesn't have to be at each one of the houses. It can be a bed of geothermal wells somewhere. But again, I suspect that in California, you wouldn't even be requiring any of these thermal wells to supplement the system. In this particular case, anyways, we're looking at the differential between putting in a geothermal, in-ground geothermal system as opposed to our sewer pipes. And for 10 houses here, there would be saving of $27,810. We're not a manufacturing company. We don't manufacture these pipes. We're basically a technology company. And we license then to other people to look after the system. So we would have concrete pipe manufacturers who would be licensed to manufacture our pipe. And there would be system installers, of course, who could be licensed to install the system. And the other thing is that municipalities could own, well, matter of fact, they own the sewer pipes in front of the house. So they could own the heating system as well. And they could then be licensed to sell the heat to collect revenue from the homeowner for the heat that is there. And this kind of slide sort of shows that there are sort of 2 things that happen with these pipes. We capture the heat from the sewage effluent in the pipes, but we also capture heat from the ground around the sewage pipes. A student at the University of Manitoba working on his master's degree did some research for us, and he determined that there is a considerable amount of heat that can be stored in the ground around the sewage pipes. And the nice thing about that is that in the hot weather, you're taking heat from your house, you're dumping it into the system, into the sewage pipe system, and into the soil around the sewage pipe. In cooler weather, then you can the system extracts that heat out of the soil around the sewage pipes. We also have, which we'll get into there shortly, a hybrid PVT, a photovoltaic thermal panel that we've developed. And with that system, you can come up with a system here where you don't have any external energy coming into your home. The sewage pipe provides the thermal energy for your home, and the PVT panels provide the electricity to operate the heat pump then that runs the system, that controls the entire system. These are some images of systems that we have installed. This is at a subdivision in Sudbury, and this is the pipes being installed And there, we also have a research facility at the local college, Cambrian College in Sudbury, and we have the PV panels, PVT system up on the wall here. And it was interesting. There was one day that Les and I went to the building to take a look at it. And I think it was -20 outside that day, Les.
Yes.
And the heat coming off of the back of the panels was 20 degrees above. So there was that was a 40-degree difference in there. And we'll get into sort of the advantages of that shortly. This is a building, maybe Les, you want to explain this building? This
this is the first zero energy building for seniors being built in Canada, and it's being built. We're using our products on it. One of the products we're using is at source energy pipe, as John has explained now, for the sewage, and we're going to be taking energy out of it and putting energy back to the surrounding area to store it in the summer for the fall and winter. We also have our at source energy panel. I'll just go over it briefly now. We call it a PVT panel, our at source energy panel, and it's photovoltaic and thermal. And we use the same principle as our at source pipe, where we have a photovoltaic panel and we have a heat exchanger behind it. And what we do is we circulate a fluid and glycol, and we take energy away, because when it's producing electricity, it's also producing heat. And one of the things, and you probably do have as a big problem in California, the more heat you have on a photovoltaic panel, the less energy you get out of it. So we take that energy away from behind the PV panel. The efficiency of the PV goes up, the electricity produces more. We're taking thermal energy out, and we can use it to heat the building or heat hot water, heat the water for the domestic hot water. Combined, we could just have it by itself like that, just for domestic hot water or heating, or we can combine it with our at source pipe, where we store the energy that we're collecting from behind the PV panels in the ground. We use the ground as a storage for energy at a later date when we need it. So that's basically what happens there. And John has just put up about the operating costs and how efficient it is. And maybe you'd like to go over that, John.
Yeah, this slide just shows that the advantage of using a system like this, but where we're using the sewage pipes as the energy system, is that there are no operating costs, and basically it's maintenance free over the entire life of the system. We've determined that there's a short calculations that we've done. There's a short payback of costs, and it's about 7.5 years. And it can also be combined with geothermal wells and fields if necessary. There's a standard ANSI CSA C448 standard for geothermal wells. We meet the requirements of that standard. As a matter of fact, that standard is currently being modified so that it will meet systems like our system. The other thing that the pipe does is, of course, it reduces peak electrical demand in the summertime because it's replacing air conditioners. You take the heat from the building in the summertime and dump it into the ground around the sewage pipes. So we're getting to the stage now where electricity demand is becoming an issue. The other thing we're going to explain here is that this what's called a fifth generation district heating and cooling system. This is sort of a schematic kind of showing the system, and it just shows red and blue lines going around a number of different structures here. But that would be a contiguous sewer pipe that would be in the ground. And the sewer pipe already is contiguous, so it's not like you're developing anything new here. The sewer pipe is already runs right down the street and around the block and everything else. So you can capture energy then from all of these various buildings that would be connected into the sewer pipe, whether it's houses or industrial buildings or commercial stores and what have you. And there can also be storage systems put along the system. The storage system could be geothermal wells, and they just supplement and boost the system as required. So at any particular point, then you can be taken, if there's excess heat in the system, it can be stored in the geothermal wells, or if it requires more heat in the system, it can be extracted from the geothermal wells. Now, the benefits are that here's a district energy system on the left side of the screen, and here's individual buildings on the right-hand side of the screen. Now, if you take a look at district energy system where they're all connected together here, I'll just show you in the next slide. Over on the right-hand side, if you have a school and houses connected into this system, the schools then are requiring heat during the day, and the homes are requiring heat normally in the morning and in the evening. By creating a district energy system like we're talking about, by using the sewage pipe to transfer heat from building to building, it flattens out the demands of this thing. In the afternoon, when the school's demanding heat, that's fine. It's drawing heat out of the system. And then later in the evening, when the homes are drawing heat out of the system, school is no longer drawing heat out of the system. So it flattens the whole system, and it's certainly less costly than putting in an individual geothermal at each one of the buildings. And with this system, you can have municipalities and wastewater utilities can become energy suppliers. So we like to say that this is the only sewage pipe around that pays for itself. At least in Northern Ontario, anyways, the sewage holes, everything costs more money because of frost in the ground and damaging and everything else. Well, our system pays for itself. It actually collects heat from the sewage that is there. And it can become a new revenue source then for energy deliverers, whether the energy deliverer is the municipality or whether a private company becomes the energy deliverer. And of course, whoever is delivering the energy can also get into the business. Just like right now, you can rent, at least in Northern Ontario, you can rent your water heater from the water supply company, or you can buy one on your own. So in this particular case, heat pumps could be rented out to the homeowners. This sort of is kind of a complex looking system right here. I'll try to explain it. We've tried to show the two systems on here. Up on the roof, we have our at-source energy panels, and they can be on the wall of the building as well. And then in the ground, we have our sewage pipe. So they're all connected together in that there is heat coming from the back of the at-source energy panels, and that heat can be utilized directly into the building, or that heat, it can be stored in the ground. And I'm sure you have this problem there, because we even have this problem in Canada, is that if people have just heat recovery panels on the building, not the photovoltaic panels, but thermal panels on the building, Les and I have driven around in the summertime, and we see that most of these panels are covered over because they're creating too much thermal energy, and people have no way to store it. Now, if you have a swimming pool or something, that's great. You can put the thermal energy into your swimming pool, but otherwise you simply have to cover them up. You can't use them. Well, in this particular case, we utilize the sewage pipe, the ground around the sewage pipe. So the heat comes from the panels and it goes down into the sewage pipe, and then it's stored in the ground around the sewage pipe for later recovery. We also tried to show on here how the electricity could be used in a on-site electricity storage system, or actually in your Tesla, I guess, the car battery as well, when you're not using it, and then the car battery ends up powering the house after that. So the voltaic, and one of the issues with photovoltaic panels is that when the panels heat up, they lose efficiency, and research has shown that they can lose about 30% of their electrical generating capacity. Not only do they lose electrical generating capacity, and this certainly would be a problem in California, not as much of a problem here in the wintertime, or certainly not today, but the heat is also destructive to building materials. Your photovoltaic panels are on the roof, and that's why you'll see the panels. There's always a gap underneath the panels when they install them for air to circulate behind the panels, but there's still a lot of that heat is still directed into the building, and heat isn't good for anything. It destroys building materials. The other problem is that heat is transferred through the walls or through the roof of your building into your building, which means that you now are trying to cool off the building. Well, you're having to cool that extra heat that is coming into the building as well. So standard voltaic panels are a problem in that sense. Now, with the PVT panels that we have, they capture this heat from the back of the panel, and they therefore eliminate this reduction of heat generation of the panel, because the panel is heating up. And also, of course, if you want to have both thermal and photovoltaic panels on your roof, well, half of the roof will have to be PV and the other half photovoltaic. With the PVT panels, you can put twice the number of photovoltaic panels on the building roof because they also function as the thermal energy panels. The panels, then you can extract the heat generated by the PV panels and store it for later use, or you can use it also as a part of your to heat the hot water system for your home. And again, by cooling the back of the panels off, we increase the efficiency of the panels. Now, I don't know if you certainly don't have this problem in Orange, California, but maybe if you get up in the mountains there and other parts, if you have any snow that gets on PV panels at all, the snow, just that there's a strip of snow across the bottom of the panels, it eliminates their electrical generation. Now, with these systems that we have, because they're connected to the fluid in the back of the panel, we can reverse it and we can put the warm water into the back of the panel, which would then melt the snow off of the panel. Again, that's a problem here, not so much there. If you take a look near the bottom of this bottom left-hand side of this sheet, you can see sort of our panels, how there are other people out there who do manufacture photovoltaic thermal panels. However, they use tubes to transfer the heat or capture the heat along the back of the panel. We use a flat plate. And when we did research, we found that with the tubes, there's very little heat transfer, or not very little, but there's certainly a lot less heat transfer between, if you lay a pencil on the table, there's little contact between the bottom of the pencil and the table, and that's where you're trying to transfer that heat through. So there's less heat transfer through to the fluid collection system on the back of the panel than there is with ours, where we have a flat plate. At the top here, you see what the panel looks like. The very top picture, the white one shows the back of the panel. You don't notice that there's anything really different. And the front of the panel is just a standard photovoltaic panel. So there's very little difference. Here's kind of a schematic of how the system might operate. There's electricity, of course, coming off the panel, which then goes to, it can be converted to AC for use in the building. And then the thermal coming off of the panel can be utilized in the domestic hot water system for your house, or it can be stored in geothermal wells or at source pipes there. In this particular case, I tried to do just a bit of a calculation of how much electricity the panels, and this is a 320, we have 10 320 watt panels here. They would generate about 6,400 kilowatt hours of electricity in Orange, California. Here, they would be calculating about 5,000 because, I'm sorry, without the heat recovery system in the back of the panels, they'd be generating about 5,000 kilowatt hours. And the thermal coming out of the panel is 43,700 kilobTUs. And I don't know what your rate is right now for electricity, but I had figured on 0.13, 13 cents for kilowatt hour. Based on that, the saving per year would be $832 of savings. The system has been recognized by geothermal magazines and what have you throughout the world. Now, how can this thing be funded? Well, a typical house emits about 7.5 tons of CO2 per year. And the at-source energy pipe has a minimum lifespan of 50 years. So over 50 years, our system would be avoiding 375 tons of CO2 per house. And we are having to start to worry about CO2 emissions. And in terms of carbon sequestration, normally it costs sorry, trying to figure out which phone was doing the ringing there. I was turning off the wrong one. Sequestering carbon costs about $500 a ton, and our system will avoid 175,000 then over the life of the system. And we took a price of $500 a ton because the carbon tax. Now, I think in California with your system there, I think you're at about right now, I think $25 a ton. I'm not sure, but I think it's in that area. And anyways, at $50 a ton over the life of the pipe, a subsidy of $17,500 can be paid to install a system by the carbon emissions that are being saved. So, geez, we're ending very early. I'm hoping there are some questions there that people want to ask.
Nothing in the chat. Anyone, if you don't feel comfortable in just speaking up, you can certainly use the chat line, or just go ahead and take yourself off mute and ask the question.
Hey, Jeff, it's Daniel. I've got one.
Mm-hmm.
Having lived in Southern Ontario, not Northern Ontario, I'm aware of this sort of system. And I've heard that in Southern California, the problem with a subterranean heat exchanger is that over time, the heat that's pumped into the soil, because we cool predominantly rather than heat, warms it up to the extent that you can no longer take the advantage of cooling the pipes down. Have you guys have comparative studies for different climate zones?
Well, that could be a problem if you have geothermal wells, for instance, or loops in the ground. In our particular case with the sewage pipe, you always have the sewage effluent flowing through that pipe. So you'll be drawing away some of that heat that is there. Now, I don't know in California how that would, how much of a problem that would be, but certainly it's less of a problem than you would have with geothermal wells or loops. Anything less?
We have the opposite problem in Southern Ontario, is that we have very few cooling days. We're not putting that much energy back into the ground. What happens there is that it creates a block of ice that never thaws out. You just have pipes embedded in the ground. The one thing with an outsourced pipe, as John was saying, it takes the energy. Energy is continually flowing one way or another. Rather, it's either taking heat with it or storing heat around it. And so that's an advantage with ours. So we haven't had any cases where in warm countries that we've had that stagnation with too much heat in the ground. But
the sort of opposite of that problem that that they have sometimes with geothermal wells is that they pull too much heat out of the ground in some areas, and they've actually had frosting around the wells and no way to defrost it. Then you have to pump energy back into the wells to defrost it. In our particular case, we have the sewage that is there that would prevent the frosting of the ground around the sewage pipes.
I have another question, if you'll tolerate it. To me, I'm just trying to calculate the volume of effluent flowing through a typical residential sewer pipe. Mm-hmm. And I'm thinking it's inherently intermittent, and it's probably concentrated at certain times of day, just like rush hour. And I'm wondering, how does it work with that sort of on-off, increasing, decreasing amount of volume?
Yeah, I mean, ideally then with the district energy system, there would be other buildings connected to it. So if you have a school, for instance, connected into it, they're operating at a different time of the day than the home would be, or hospitals or industrial buildings. But probably when assume that people turn the heat up or whatever, cool, or turn the cooling down when they're not home, or when they're home. So that's the same time they're using the tubs and showers and everything else in the building. So I think in that particular case, the two of them may match to an extent.
Yeah, and the one advantage with ours is that our heating system is around the whole pipe. I know that we're using the ground as a storage energy, and so we're leveling it out. There are some systems out where they have a plate just in the bottom of the sewer pipe, and there has to be effluent in the pipe in order to get energy out or put energy back into the effluent. Ours, we have it continually around the pipe, so circulating around the whole pipe, the concrete sewer pipe. And so we're using the ground as a medium back and forth for heat storage also. So it levels out that we don't have the peaks and the valleys as much.
The ground basically becomes a buffer. Are there any other questions?
We do have a question in the chat from Frederick Crooks. What is the cost per watt for the PV thermal panels?
Les, do you have that?
Well, a typical 400 watt PVT panel runs around $700. Now that price has been coming down. It started off at about 1,100, so the 700 probably, as the PV continues to get cheaper and cheaper, and the thermal panel, we hope to get it down around the 500, so a little over $1 a watt. Now remember, we're talking about the PV component is $1 per watt for the PV, but we're getting 4 to 5 watts of thermal out of that also. So we're paying $1 for the total energy package of 4 to 5 watts. So it's fairly cheap. It brings it down quite to quite a reasonable price.
When we did calculations, we found that just like the sewage pipe, there's about a 7.5 year payback on the system.
And that's why it's so cheap.
Any other questions at all?
Nothing in the chat.
Pardon me?
There's nothing else in the chat right at the moment.
Oh, nobody has any verbal questions?
Yeah, and if there's any more detailed questions, detailed answers that you'd like, you could, I'm not sure how you're doing it in the course, but you could text us or email us and we could provide you with more detail.
Yeah, with the last slide that you're looking at on the screen right now, it has the how you can contact us to find anything out. I think like one of the real advantage probably in California, both of the systems is that you'd be capturing heat then that could be used in swimming pools. Because from what I understand, talking to people with pools there, no matter what the temperature is, you always need some extra heat for the swimming pool. Now that heat could go through a heat pump, or it could go perhaps directly into the pool to heat it up.
Or just a straight heat exchanger, very cheap.
So with the PVT panels, for instance, you could the electricity that the panel is generating would probably be sufficient to, well, would be sufficient. You could design it so it's sufficient to run the pump, and then the heat coming from the back of the panel might be sufficient then to heat the pool in the cooler periods of time. No other questions?
I guess I could ask a question. Are there any incentives in California for solar?
I don't know, but I think Daniel might actually have some of those answers. He has been putting on some programs for his firm and also for AIA Orange County. And I hate to put him on the spot, but if he's available, maybe he can respond.
Hey, Jeff, sure, I'll take a shot at that. And I'm going to mold it to something I'm very concerned about at the moment. In California, there is kind of a latent disagreement and debate going on between distributed infrastructure and concentrated or aggregated generation facilities, i.e. a giant solar field somewhere versus a million rooftops. And there's actually legislation pending in the state legislature that's being pushed by the utility companies to reduce the amount of money that the utility pays when I, for example, because of my generation exceeds my own needs, I'm feeding it back into the grid. They're proposing to reduce what they pay me for my power by 70% in California, which I think will terminate the million household solar program. I'm wondering if guys are aware of that. I think that's policy.
Yeah, I've heard about that. Yeah.
Because there are still state rebates available for solar systems because it takes the rebate for most people to make it pencil. So I don't think that's threatened. It's just that the amount so the capital for the startup cost is about the same, but what's threatened is your sort of life cycle cost because of the reduction of the fare you're getting back from the utility.
That's what happened in Ontario. It started off at small consumers could install solar and they would subsidize it. And then it went to these big corporations coming in from out of the country and building these huge solar farms. And all the money went to them and they received all the incentives and then they left. And a lot of these farms are operating at very minimal value that they could be. And so the government, they took all the government's money and led the country. So probably the same thing will happen in California, rather than give it back to the consumers individually, which, you know, you get 1 million of them, you have a lot of energy being produced. It helps everybody. And especially with our panel, if you added on the thermal component, where you could store the energy and use it to heat your hot water or your pool or whatever, it would really be of value. That's too bad they're considering that.
And I hear a lot of cities in the States as well. I think in New York in particular, they're actually going to disallow natural gas as an energy source because of the carbon emissions issue. So I don't know what that is going to do. I don't know how that is in California right now.
There are several municipalities in California that have also outlawed natural gas anything. And that's just the camel's nose under the tent. So within some, you know, foreseeable time of the future, the whole state will probably adapt that as well.
Yeah. So, you know, right now there are a lot of things preventing the use of green energy or slowing down the use of green energy because, you know, in a lot of cases, certainly in Canada here with our tar sands and that, there are a lot of subsidies for alternative or for carbon-based energies. But that is starting to change as people become more aware. And I think people are becoming more aware as we get into some of the terrible weather that we've had this year in a lot of areas. You know, all of a sudden, the global warming is becoming more real to a lot of people than it was in the past.
Let's see, I see a couple more. Let's see if these are questions. Nope, thank you for the excellent presentation. We have several of those written in here.
Okay, no other questions? Well, if anybody would like any more information, feel free to contact us. We're a small company here. We've been sort of in this for quite a while now, less trying to promote the product and do more research. And we're slowly getting into buildings now where we're putting in our system, do a little bit of research and collect more data on it. As a matter of fact, right now we're looking at, you know, we've been talking about the PVT panels where we've been putting a fluid behind the panels. We're now looking at a system as well where we use a gas behind the panels as opposed to a fluid. Maybe Les, if you want to explain that a little bit.
Yeah, you know, some of the heat pumps, in fact, you can use 410 gas. That's what we use here. And one of the things what we're using, we think we'll have more efficiency if we circulate the gas through the piping or the exchange panel behind the PV. And we can get more energy out and from behind the panel. And the more energy we can take out, again, the more efficient is the photovoltaic part of it, the electrical part. So that's where we're looking at right now.
Yeah, so we're always interested in potential research projects that anybody might have as our demonstration type projects to show what our system can do and to collect more information on the system.
We do have a comment. Betsy Daugherty was giving us an update that California is heading for no gas and all electric for new construction.
Oh,
Yeah, yeah.
Also, of course, Jeff, California has outlawed the sale of combustion engine vehicles as of either 2030 or 2035. I can't remember what year it is. So that there's a kind of a collision happening here between demand and supply.
Yeah, we're heading in that direction as well. I'm not sure where all the little generation stations to power up the vehicles are going to be, but we'll see what happens there, I guess.
most of the batteries for the electric cars with the nickel component and the cobalt comes from the Sudbury area. So it'll be interesting.
So Les, what you're saying is you guys were in on that.
Yeah, I think so.
Yeah, okay, all right.
And there's another follow-up response from TAN. You can receive incentive for gas and electric. The incentive is higher on all electric for new construction.
Oh, okay.
Oh, good.
So are those incentives, would that include photovoltaic panels at all, or?
That I don't know.
It's the incentives are whole energy model design based. So if you include photovoltaics, you can technically deduct that off of your baseline of the strategy of how much energy you're going to be consuming, essentially.
Just as a side, I used to watch Bill Mayer. I don't know if you know his program or not on TV, but I think he was in Los Angeles somewhere, and Bill Mayer, I think it took him 2 years or something. I think he had his PV all there, but it took 2 years before he could get the authority to hook it up.
So like a combination of our PVT panels, that would be ideal in order to get the energy consumption, the carbon-based consumption down when you're designing new buildings. If that's the case, they'll probably base it on the amount of CO2 that you're saving or carbon you're saving.
One thing we didn't mention is when you do go to utilizing any green energy systems for homes, a lot has to be put into the design of the home as well. So that means better insulation and better heat retention within the building, I think, which stands as a given, I suppose. Well,
Thank you.
thank you, folks.
Yeah, thank you. That was excellent.
So thank you very much. Again, if you have any questions, contact us.
Well, I just stop share here.
Yeah, you can stop share. I'm just hanging out. It's okay. We still have a lot of people on here. Possible a question may come up, but I'll just wait until it gets down to the three of us.
Mhm.
These Canadian embassy programs have really been great. Not just great for us, but it's wonderful to offer these types of products and services that are from out of the country for smaller firms such as yourself. That's kind of how this all came together. I want to say 4 years ago. And as Marilee mentioned, it'd be a 1-day program, and we'd have maybe 5 different speakers throughout the day. And then, of course, they all went virtual, and they've all been very, very interesting. So thank you.
Mhm. Yeah, personally, I'm not crazy about doing virtual presentations, but I guess you get used to it after a little while if you did enough.
Yeah, that's right. I mentioned earlier, it's usually when I'm presenting like a national AIA, stuff like that, that's when the cat decides to walk across. And 2 years ago, when this would go on, or the dog bark, you'd apologize, you felt bad. Yeah, it's just like, yeah, whatever. We're all used to it at this point.
Yeah. Oh. We haven't had too many of these with virtual presentations. A lot of virtual meetings, of course, but not many virtual presentations. So